Fine. Let's start. Somewhere in the constellation Boötes, there is a hole. Not a black hole. Not a nebula. Just nothing. A spherical region of space roughly 330 million light-years across where, if you went looking for galaxies, you'd find almost none. Where astronomers expected to find around 2,000 galaxies, they found 60. 60. In a region so vast that if you tried to cross it at the speed of light, it would take longer than the current age of the Earth. Times 60. Here's the comparison that actually breaks your brain. If the Milky Way had been sitting at the center of the Boötes Void instead of where it is now, we would not have discovered that other galaxies existed until the 1960s. We would have looked out into space for all of human history and seen essentially nothing. No Andromeda, no Virgo cluster, no hints of a larger universe, just our galaxy floating alone in what appeared to be an infinite empty dark. The official explanation is that many smaller voids merged over billions of years to create this one enormous absence. Fine, that makes sense on paper. But here's the thing. That process, voids merging into supervoids, has never actually been directly observed. We have a mechanism. We just haven't watched it happen. The Boötes Void is real. It's right there. And the universe does not seem to care whether we understand it or not. The void doesn't announce itself. It has no edge you could point to, no wall, no boundary marker. It's just space becoming quieter and then quieter still, until there's nothing left to listen to. Number 9. 11 billion light-years away, when the universe was less than 2 billion years old, something was already building. The structure is called Hyperion, named after the Titan of Greek mythology, which is appropriate because it is enormous in a way that the early universe simply should not have been capable of producing. It's a proto-supercluster, a web of 7 dense peaks of galaxies connected by filaments of matter stretching roughly 490 million light-years at its largest dimension. Its total mass is approximately 4.8 quadrillion solar masses, around 5,000 times the mass of the entire Milky Way, all tangled together, already forming when the universe hadn't even finished its adolescence. The team that found it used an instrument on the Very Large Telescope in Chile that could measure the distances to hundreds of galaxies simultaneously. And when they plotted what they had, they got Hyperion, sitting there, fully assembled or close to it. Already vast, already complex, in a universe that, according to our models, shouldn't have had nearly enough time to build something like that yet. But here's the thing that really lingers. Hyperion is not just a historical curiosity, it's a prediction. Astronomers think that over the next several billion years, it will collapse inward under its own gravity and slowly evolve into something that looks a lot like our own cosmic neighborhood, the structures we live in right now. Which means when we look at Hyperion, we might be looking at an ancestor, a blueprint, the early draft of a universe that eventually produced us. The universe was building cathedrals before the mortar had even set. Number 8. About 4 billion light-years from Earth in the direction of the constellation Pisces, there is a structure called the Saraswati Supercluster. It's named after the Hindu goddess of knowledge, which is a genuinely beautiful name for something this large, and it was discovered entirely by an Indian research team, a notable first at this scale. Here's what it is. A wall of galaxy clusters, roughly 650 million light-years long, containing at least 43 massive clusters, and a total combined mass of roughly 20 million billion times the mass of our Sun. If you picked up the entire Milky Way and used it as a unit of measurement, Saraswati would weigh something in the neighborhood of 20 billion of those. Now, size alone doesn't make Saraswati strange. What makes it strange is when it exists. It sits at a distance where, because of the speed of light, we're seeing it as it was roughly 4 billion years ago. That means this structure formed and survived during a period when dark energy was already actively working against the formation of large-scale structures. Dark energy is the force responsible for the accelerating expansion of the universe. It fights gravity, it pulls things apart. It is, in a very literal sense, the enemy of large cosmic structures. And yet here is Saraswati, massive and intact, sitting in an area when it probably shouldn't be. The mainstream answer is that it's marginally consistent with models, just at the edge of what's expected, which is a polite scientific way of saying we're not entirely sure how it held together this long. Some things in the universe are stubborn like that. They exist simply because no one told them not to. Number 7. In 2020, astronomers announced the discovery of a galaxy filament at least 1.4 billion light-years long, comparable in size to some of the largest known structures in the universe, only half the distance away from us as the Sloan Great Wall, and we had absolutely no idea it was there. It's called the South Pole Wall, and the reason it went undetected isn't exotic, it's almost embarrassing. Part of it hides behind the Milky Way itself. Our own galaxy, with all its dust and gas and stars, sits in the way like a hand accidentally blocking a photograph. The region is called the Zone of Galactic Obscuration, and for a long time, it was simply a blind spot in our map of the universe. What makes this discovery remarkable is how they finally found it. They didn't see it, they felt it. By mapping the peculiar velocities of galaxies, the small deviations in how they move, caused by the gravitational pull of nearby mass, the team was able to infer a structure behind the veil, the way you might deduce the shape of something hidden in fog by watching how the air around it moves. And then, after all that, the lead researcher on the paper said something quietly alarming. We don't know how big it actually is. The mapped portion stretches more than 200 degrees across the sky, more than a semicircle, more than half the observable dome above us. And it keeps going into the obscured zone. The edges are still unknown. One of the largest nearby things in the universe was invisible until 5 years ago, and we still haven't seen all of it. Number 6. Until 2014, we didn't know where we lived. That sounds absurd. We know the Earth is in the solar system. The solar system is in the Milky Way. The Milky Way is in the local group. The local group is in the Virgo Supercluster. Astronomers had known about the Virgo Supercluster for decades. Job done. Except it wasn't. In September of 2014, astronomer R. Brent Tully of the University of Hawaii and his colleagues published a paper that essentially redrew our cosmic address. By mapping not just where galaxies are, but how they move, specifically the way gravity causes them to drift toward concentrations of mass, they identified our true home supercluster. They called it Laniakea. In Hawaiian, it means immense heaven. Laniakea is 500 million light-years across. It contains 100,000 large galaxies. It includes the Virgo supercluster, the Centaurus supercluster, several others. All of them now understood to be subcomponents of something far larger that we had simply never recognized as a single structure. The Milky Way sits near its outer edge, like a house on the outskirts of a continent-spanning city. Here's the thing, though. Laniakea isn't held together by gravity. It's not gravitationally bound. Which means it's not really a permanent structure. It's more like a temporary eddy in the cosmic flow. Dark energy is already pulling it apart. The 100,000 galaxies that share our home supercluster are, right now, slowly drifting away from each other. We live in something vast and magnificent and dissolving. We named it immense heaven. Turns out, immense heaven doesn't last forever either. Number 5, 380,000 years after the Big Bang, the universe did something strange. Before that point, it was so hot and dense that matter and radiation were locked together. A glowing, opaque plasma, like the inside of a star, everywhere, in every direction, forever. And then it cooled, just enough for atoms to form. And all that trapped energy, all that pressure, released. As sound. A sound wave. One single enormous ripple of pressure propagating outward through the early universe at roughly half the speed of light. It traveled for 115,000 years, and then the universe cooled further, and the wave froze. Stopped dead. Preserved in the structure of matter itself, like a ring in a tree trunk, like a fossil imprinted in stone. That frozen wave is called a baryon acoustic oscillation. We've confirmed its existence many times through statistical surveys. It shows up as a slight preference for galaxies to be separated by a specific distance, about 500 million light-years. It's one of the most elegant confirmations of the Big Bang model we have. But in September of 2023, R. Brent Tully, the same astronomer who gave us Laniakea, announced something extraordinary. He thought he had found a single individual baryon acoustic oscillation, an actual, distinct physical shell of galaxies. 1 billion light-years across, still visible, still there. They named it Hoʻoleilana from a Hawaiian creation chant, sent murmurs of awakening. And here's the detail that makes your stomach do something. The Sloan Great Wall, which was itself considered one of the largest known structures in the universe when it was discovered in 2003, a filament of galaxies 1.4 billion light-years long, sits on the rim of Hoʻoleilana. It's debris on the edge of a wave that has been traveling since the universe was 380,000 years old. We are not just riding a sound wave from the Big Bang. We are living close enough to see its wake. Number 4. Here is a question that sounds simple. How fast is the universe expanding? Astronomers have two ways to measure this. The first is to look at the early universe, specifically the cosmic microwave background, the faint afterglow of the Big Bang, and calculate the expansion rate from first principles. The second is to measure it directly, right now, using nearby stars and galaxies as distance markers. Both methods are precise. Both methods are reliable. They get different answers. This discrepancy, called the Hubble tension, is one of the biggest open problems in modern physics. It shouldn't exist. If our model of the universe is correct, both methods should agree. They don't. And nobody knows why. Now, what if the reason they don't agree is because of where we are? In 2013, a team at the University of Wisconsin-Madison found evidence that the Milky Way sits near the center of a vast underdense region, a cosmic void roughly 2 billion light-years across, where matter density is 20 to 30% below the cosmic average. Not empty like the Boötes Void, just thin. Like a low-pressure system in the atmosphere. They called it the KBC Void, or sometimes simply the local hole. Here's the implication, and it's a big one. If we're sitting in an unusually underdense region, gravity works slightly differently around us than it does in the average part of the universe. Galaxies near us are being gently pushed outward by the surrounding overdensity, like water draining away from a depression, which means the local expansion rate we measure is slightly inflated relative to the true cosmic average, which means the Hubble tension might not require new physics at all. It might just require acknowledging that we live in a hole, a very large hole. A hole we can barely see the edge of. The universe doesn't let us stand on neutral ground. Apparently we never had it. Number 3. In 2021, a PhD student named Alexia Lopez was going through quasar data from the Sloan Digital Sky Survey. She was looking at how background quasars get dimmed by magnesium gas along the line of sight, a technique for tracing matter between us and very distant objects. And in the data, she noticed something. A crescent. A smile. A curved arrangement of absorbers stretched across the sky that seemed to form a coherent arc. She measured it, checked it again, had her supervisor check it, and eventually, with a statistical significance of 4.5 sigma, she announced it. The giant arc. A crescent-shaped structure 9.2 billion light-years away and 3.3 billion light-years long. 1/15 the radius of the observable universe. If you could see it with the naked eye, it would span roughly 20 times the width of the full moon. The theoretical maximum size for any cosmic structure, according to the cosmological principle, is about 1.2 billion light-years. The giant arc is nearly 3 times that. Then, in January of 2024, Lopez announced a second structure, the Big Ring. Same distance, same patch of sky. A ring-shaped arrangement of galaxies roughly 1.3 billion light-years in diameter, statistical significance 5.2 sigma. Found the same way, by the same person, sitting right next to the first impossible thing she found. 2 structures, both larger than the theoretical limit, same location, same distance, found by the same researcher at a small UK university who happens to be supervised by Roger Close, the man who in 1991 discovered the Claus-Campusano Large Quasar Group, and in 2013 co-discovered the Huge Large Quasar Group, another record-breaking structure. Nobel laureate Jim Peebles looked at the Big Ring and the giant arc and said they might be real and significant. Here's the thing, the debate is still live. A 2025 paper argued that patterns like these appear in statistically homogeneous universes more often than expected, and that the linking method used to define the structures was flawed. The original team responded, "Nobody has conceded. The science is not settled, but even if you're skeptical and reasonable people are, the pattern here is strange. One small team, one small university. Over 3 decades, a string of structures that keep pushing against or past the theoretical limit of what should exist. That might be selection bias, it might be a quirk of their methods, or it might be that they're standing in a part of the data that everyone else walked past. Sometimes the universe hides its strangest secrets in a curve that looks from the right angle like a smile." Number 2. For a while, astronomers were puzzled by something they called the Great Attractor. Galaxies don't just sit still. They have peculiar velocities, small gravitational drifts that deviate from the general expansion of the universe. And in the 1980s, astronomers noticed that our entire local region of space, the Milky Way, the local group, the Virgo cluster, hundreds of thousands of galaxies, was drifting in a specific direction towards something in the constellation Centaurus, something massive, something pulling. They called it the Great Attractor, and for years it was genuinely mysterious, partly because it sat almost exactly in the plane of the Milky Way, right behind all that obscuring dust and gas, making it nearly impossible to observe directly. When they finally got better X-ray and radio telescopes that could peer through the obscuration, they found galaxy clusters in that direction. Significant mass. A real overdensity. But it was about 1/10 the mass they had expected. Nowhere near enough to explain all the motion they were seeing. The Great Attractor wasn't the attractor. The real engine was behind it. Further away, mostly hidden. A structure called the Shapley Supercluster, sitting roughly 650 to 780 million light-years from Earth. Hundreds of galaxy clusters. A total estimated mass of somewhere between 10 and 26 quadrillion solar masses. The single most massive known structure in the local universe. Everything in our region of space is falling toward Shapley. Not fast, cosmologically speaking, it's a slow drift, a gravitational inevitability playing out over billions of years. But the direction is set. The Milky Way has a destination. Every galaxy in our supercluster has a destination, and that destination has been quietly pulling at us since before the Earth existed. We spent decades puzzling over the wrong thing. The Great Attractor was just the shadow of something much larger sitting behind it. And somewhere, improbably far away, Shapley waits. Number 1. In November of 2013, a Hungarian-American research team announced a discovery that has not stopped being uncomfortable ever since. They were studying gamma-ray bursts, the most energetic explosions in the universe, visible across billions of light-years, useful as cosmic distance markers. And they noticed that a particular group of these bursts, at redshifts between 1.6 and 2.1, seemed to be clustering together in a way that was statistically improbable. Not random, organized, connected. When they mapped it, what they found was a structure, or at least an apparent structure, spanning somewhere between 10 and 15 billion light-years. The research was announced publicly in 2014, and the structure was named somewhat unexpectedly by a Filipino teenager online. The name that stuck. The Hercules Corona Borealis Great Wall. Let's hold that number for a moment. 10 to 15 billion light-years. The observable universe, the total sphere of everything we can in principle see, is about 93 billion light-years across. The HER-CRB Great Wall would be, by the most recent estimates, up to 1/6 of that. One structure. Possibly 1/6 of everything. Now here's the thing that actually matters, so not just the size, but what the size means. Modern cosmology is built on something called the cosmological principle. It's a foundational assumption baked into Einstein's field equations, baked into every major model of the universe we have. The principle states that the universe, at large enough scales, is roughly the same everywhere. Smooth, uniform, no special regions, no giant clumps, no gaping voids. Just an even distribution of matter that, when you zoom out far enough, looks the same in every direction from every location. And this isn't just an aesthetic preference, It's a mathematical necessity for our equations to work the way they do. Without it, the standard model of cosmology, the one that makes predictions we can test, the one that correctly described the Big Bang and the formation of galaxies, and the expansion of the universe, becomes much harder to justify. The theoretical upper size limit for any cosmic structure set by this principle is roughly 1.2 billion light years. The Hercules Great Wall is approximately 10 times that, maybe more. Now, the skeptics are not wrong to be skeptical. The structure is inferred entirely from gamma-ray burst positions. It's not a direct galaxy map. The dataset, even after a 2025 reanalysis of 542 gamma-ray bursts, is still relatively sparse. Some of the apparent clustering could be explained by telescope biases, dust, imprecise distance measurements. It is genuinely possible that with better data, the structure dissolves into noise. But here's what doesn't dissolve. The Hercules Great Wall is not alone. The giant arc, the big ring, the huge large quasar group, the boss. Great Wall. Structure after structure sits at or beyond the theoretical limit. Not one anomaly, a pattern of anomalies. Each one individually dismissible, maybe. All of them together, that requires a different kind of attention. The cosmological principle is supposed to be the floor, the thing you stand on while you do cosmology. And right now, the universe seems to be doing something to that floor. Not breaking it exactly, but flexing it, testing it, producing edge cases and anomalies, and structures that fit inside the model if you allow the model just a little more flexibility than it used to have. Maybe the principle holds and we just need better data. Maybe it holds approximately but not perfectly, which is a subtly different and much more interesting problem. Or maybe we are living through the early stages of a major paradigm revision, the kind that happens every few generations in science, where the map turns out not to match the territory in some fundamental way. The universe doesn't announce these things. It just keeps producing data. It keeps building structures that make us look up our own equations and quietly wonder whether we wrote them down right. We have a model of the universe, a beautiful one, an elegant one that has survived decades of testing and made predictions that came true. And then there's whatever this is. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.